So as usual, just take a moment to make sure that you're comfortable and that you're calm and focused and ready to do maths for a little bit. So one of the things that it's worth thinking about is what kind of answers do we want to get when we're looking for a particular set. What do I mean? Suppose we're looking at the set of all x which solve the equation 81x to the 4 minus 16 equals 0. Well, the elements that end up in A will depend very much on what kind of numbers we're looking for. So for example, if we're only allowing integers, then there are no integers which solve that equation, so our set A would be the empty set. But if we solve that equation and we're fine with getting rational numbers for our solution, then we do actually have some elements in our set A. We would have 2/3 and minus 2/3. But if we go even further and say, okay, well, we will take any answers that are complex numbers, then we get even more answers. So we have the two rational ones that we've already seen, and we also get two complex solutions. So our A has grown in size to 4. We have a way of talking about this. We say that the universe, or the universal set, is a set of all elements under discussion for possible membership in a set. So if we go back to our previous example, when we were only allowing integers here, our universe was the integers. We allowed rational numbers, our universe was the rational numbers, and we'd write that u is equal to the rational numbers. And if we're allowing complex numbers, then we'd say our universe is equal to the complex numbers. So whenever we see a u, we're talking about all the possible things that an element might be in a set. A useful thing when we're thinking about sets, particularly when we have more than one set, is to have a visual representation. And one way of visualizing is using a Venn diagram, which I'm sure you saw while you were still in school. So in the Venn diagram, our universal set is represented by a rectangle, and any subsets are circles within it. So if, for example, we have that our universal set is the integers, and the set that we're interested in is 1, 2, 3, then our Venn diagram would look something like this. So here's a rectangle that's representing our universe. So this is our universe, which is integers. And then we'd put a circle inside, which we label A, and we can put the elements 1, 2, and 3. Now, there are lots and lots of ways of combining two numbers to get a third number. For example, we can add the two numbers, we can multiply, and so on. And in fact, it turns out that there are many ways of combining sets to get new sets. We're going to look at several of those now. So one idea is to think about what happens when we have two sets, and we want to find any elements that are in both of the sets. This notion is called the intersection, and the symbol that we use is this little downward facing U. So the intersection of sets A and B is the set of all x such that x is an element of A and x is an element of B. If you want to show this on a Venn diagram, we put our universal set, whatever that might be, and then we show our two sets A and B, and we're showing that they're overlapping a little bit, although they might not have any intersection. And then in order to show that we're thinking about the intersection, we shade in the bits where they overlap. So that overlapping bit is A intersection B. It's worth noting that in some other textbooks, people shade what is not included, but for us, we're going to shade what is included, what we are thinking about. Alright, so let's do some calculations. We've got two sets here. We've got A is equal to 1, 3, 8, and B is equal to minus 9, 22, 3. And we'd like to calculate the intersection of A and B, which means finding all the elements which are common to both A and B. So if we work through A, we have, look, A's got a 1, but B doesn't have a 1, so we're not going to have 1 in our intersection. A has a 3 and B has a 3, so 3 will be in the intersection. A has an 8, B doesn't, so in fact our intersection is just 3. We've obviously spent some time in or past mathematical history solving systems of linear equations, and we can actually think about solving a system of equations as finding an intersection. For example, solve x plus y equals 7 and x minus y equals 3. Well, we can write this as a set intersection. So we're going to start by saying, let the set A be the set of all points x, y, such that x plus y equals 7. So A is really just the straight line x plus y equals 7. And we're going to do the same thing for B is equal to the set of all points x, y, such that x minus y is equal to 3. Now if you go ahead and solve that differential, if you go ahead and solve that equation, you'll see that the solution that you get is in fact the intersection of these two, which is 0.52. A couple of points to ponder. So intersections may include all of one of the sets. For example, if we look at the intersection of integers and the rational numbers, then this is going to be all of the integers. And this is because we have that the integers are contained in the rational numbers. On the other hand, it could be that an intersection is empty. For example, if we let our set A be 3, 5, 9 and B 2, 4, 6, then they don't have any elements in common, so the intersection is the empty set. We have a way of talking about that. If we have two sets who have no elements in common, then we say that those sets are disjoint. So that's just a little bit of terminology. So we've thought about what happens when we're looking for two sets and what they have in common, but sometimes we might want to think about the elements which are in either of the sets, or rather the combination of all the elements. Remember, we remove duplicates because we don't have duplicates in sets. In this case, we define the union, so the union of A and B, and we use an upside down, a little u to indicate union. The union is the set of all elements that are in A or B. And in set notation, we write it like so. So what does our Venn diagram look like if we're going to sketch the union? Well, we've got our universal set, and again we have A and we have B, and our union is going to be everything that's in A or B. So just working through a quick check, so we've got A is 1, 2, 3, B is 4, 5, 6, then our union of A and B will be all the elements of A and all the elements of B. Thinking about integers and rational numbers again, if we look at the union of the integers and the rational numbers, that's just going to be the rational numbers. And again, this is because by taking the union with the integers, we're not getting any additional numbers. The rational numbers give us everything we have. So this is because our integers are contained in the rationals. On the other hand, if we take the union of A and the empty set, then we're just going to get A back again, because we're not getting any more elements from the empty set. So another thing that we might want to think about is if we've got two sets A and B, then what elements are in B that are not in A? So we've talked about which ones they have in common, but now we want to think about which ones are specific to B. So this is called the complement of A relative to B, and there are two types of notation that you'll see, either B minus A or B with a slash A. And if we want to write this in set builder notation, B minus A is the set of all x, where x is an element of B and x is not an element of A. So let's just take a moment to draw the Venn diagram for that. So we've got our universal set, we've got our set A, we've got our set B, and what we're interested in is just the elements that are special to B. Now sometimes we are thinking about a universal set and a subset within that. In that case, we, instead of writing U minus A, we say A with a little c at top, and that stands for the complement of A. So when we've got two sets, we talk about the complement of A relative to B, but if we're talking about the universal set and some set, then it's simply the complement of A. So if we want to do the sketch of that, here's our universal set, here's our set A, and the complement of A is everything that's in the universal set but that isn't in A. So it's everything. Oops, there we go. So here we have some of the examples from the textbook that it's worth thinking about. If our universal set is the numbers 1 through 10, A is our even, then the complement of A is the odd numbers. And if you think about going the other direction, so we're thinking here A minus U, so which elements are in A but not in the universal set? Well, since A is a subset of the universal set, that's going to be the empty set. Spend some time having a look through the rest of these examples and make sure that you're comfortable with them. So yet another idea is the idea of the symmetric difference. So the symmetric difference of A and B is a set of all elements that are in A and in B, but not in both. So let's draw a Venn diagram of that and check that it makes sense. So here we've got our set A, we've got our set B, and what we want is elements that are in A or in B but not in both. So we're really wanting to exclude the intersection. So the elements that we want are these ones. I think we should probably actually have an OR here. So this is a set of all elements that are in A or B but not in both. And you can write this using unions and intersections. So if you think about what we're doing, our symmetric difference, which is indicated by this plus sign in a circle, it's A union B minus the intersection. So if we have a look at our sets A equals 1, 3, 8 and B equals 2, 4, 8, easiest to think about this as A union B minus A intersection B. So let's work those out. So A union B is going to be 1, 2, 3, 4, and 8. And the intersection of A and B is going to be 8. So our symmetric difference is going to be 1, 2, 3, and 4. So let's think about what happens if we've got any old set A and we're taking the symmetric difference with the empty set. Well, we want all the elements that are in A that are not in the empty set, and all the elements in the empty set that are not in A. Well, there aren't any elements in the empty set, so we must just get A back. On the other hand, if we look at the symmetric difference of A with itself, well, we need all the elements of A that are not in A, and that is obviously going to be the empty set, because there are no elements that are in A that are not in A. We can also think about the symmetric difference of the real numbers and the rational numbers. So we want all the real numbers that are not rational numbers, and that'll give us irrational numbers, and all the rational numbers that are not real. Well, we're not getting any additions there. So this is a set of irrational numbers. So we have one more way of combining two sets to give another set, and that's called the Cartesian product. And the idea here is that you've got two sets, A and B, and the Cartesian product is a set of all possible pairs of elements from A and B, where the first element comes from A and the second comes from B. So let's just have a look at an example. If we've got A is 1, 2, 3 and B equals 4, 5, 6, we want all the possible pairs where the first element comes from A and the second component comes from B. So let's go for this. Alright, so if we have a 1, so we're taking the 1 from the A, then we can either have 1, 4 or we could have 1, 5. Those are the two pairs which we can create, which start with a 1. And we have, starting with a 2, we can either have 2, 4 or 2, 5, and then we can have 3, 4 or 3, 5. So those are all our possible pairs of numbers where the first one comes from A and the second one comes from B. And just to do a quick check, we could also take the Cartesian product of B with itself, in which case our first element, if it's a 4, then we can have 4, 4, or we can have 4, 5, or we can have 5, 4, or 5, 5. It's worth noting that if A and B are finite sets, then the size of the Cartesian product is just the product of the cardinalities of A and B. So notice here how mathematicians reuse symbols. This symbol over here is meaning Cartesian product, and it's talking about how can you combine sets, but over here we're using the same symbol, but this is just the usual multiplication of numbers that we've been using for years.